We've now reached the section From the Perceptron to Support Vector Machines. In this section we'll discuss a powerful discriminative model for classification and regression called the Support Vector Machine, SVM. First, we'll revisit mapping features to higher dimensional spaces. Then we'll discuss how SVMs mitigate the computation and generalization problems encountered when learning from data mapped to high-dimensional spaces. We'll try to develop an intuition of how SVMs work in order to apply them effectively with Scikit-learn. Now we move on to the first video of this section that deals with kernels and the kernel trick. In this video we're going to discuss why the kernel trick is used and how it's used. We'll learn about the problem caused by mapping to high-dimensional features. The perceptron separates instances of the positive class from instances of the negative class using a hyperplane as a decision boundary. The decision boundary is given by this formula. Predictions are made using this function. This expression of the model is called the dual form. The expression we used previously is the primal form. The most important difference between the primal and dual forms is that the primal form computes the inner product of the model parameters and the test instance's feature vector, while the dual form computes the inner product of the training instances and the test instance's feature vector. We can map the data to a higher dimensional space by applying the mapping to the feature vectors with these equations. As noted, this mapping allows us to express more complex models, but it introduces computation and generalization problems. Mapping the feature vectors and computing their dot products can require a prohibitively large amount of processing power. Fortunately, there is a method called kernel trick. A kernel is a function that, given the original feature vectors, returns the same value as the dot product of its corresponding mapped feature vectors. Kernels do not explicitly map the feature vectors to higher dimensional space or calculate the dot product of the mapped vectors. Kernels produce the same value through a different series of operations that can often be computed more efficiently. Kernels are defined more formally in this equation. Let's demonstrate how kernels work. Suppose that we have two feature vectors, x and z. In our model, we wish to map the feature vectors to a higher dimensional space using the displayed transformation. The dot product of the mapped normalized feature vectors is equivalent to this. The kernel given by the formula produces the same value as the dot product of the mapped feature vectors. Let's plug in values for the feature vectors to make this example more concrete. The kernel, k, x, z, produced the same value as the dot product of the mapped feature vectors, but it never explicitly mapped the feature vectors to the higher dimensional space and required fewer arithmetic operations. Scikit-learn provides several commonly used kernels, including the polynomial, sigmoid, Gaussian, and linear kernels. Polynomial kernels are given by this equation. Quadratic kernels, or polynomial kernels where k is equal to 2, are commonly used in natural language processing. The sigmoid kernel is given by this equation. Gamma and r are hyperparameters that can be tuned through cross-validation. The Gaussian kernel is a good first choice for problems requiring non-linear models. The Gaussian kernel is a radial basis function. A decision boundary that is a hyperplane in the mapped feature space is similar to a decision boundary that is a hypersphere in the original space. The feature space produced by the Gaussian kernel can have an infinite number of dimensions, a feat that would be impossible otherwise. The Gaussian kernel is given by this equation. It's always important to scale the features when using SVMs, but feature scaling is especially important when using the Gaussian kernel. Choosing a kernel can be challenging. Ideally, a kernel will measure similarity between instances in a way that's useful to the task. While kernels are commonly used with SVMs, they can also be used with any model that can be expressed in terms of the dot product of two feature vectors, including logistic regression, perceptrons, and principal component analysis, PCA. This brings us to the end of this video. Cool.